Greetings, everyone. Dr. D from ACU here. Today it's time to talk about forces. That's right. So, the way I want to start thinking about this is with a very simple, practical, everyday question that physics can help us with. How do you go about landing a 2,000-pound nuclear powered tank on the surface of Mars? Now, just so you have a sense of scale here, let's talk about the Curiosity rover. So, here we have a display of all the robots that are cruising around Mars right now. We've got this cute little guy that's the size of a puppy, and we've got this guy. I'm talking about the Curiosity. Now, these two people in lab coats, they're not crawling around Mars right now, but Curiosity, the giant six-wheeled nuclear-powered tank with a freaking laser mounted on its head to blast rocks apart to measure their chemical composition. How do you actually go about doing that? Well, there's an amazing video I'd love for you all to see. I'll put the link in the description, or you can click on it here. I would really encourage you to stop and watch this for a second and think about the forces required to make this happen. So the short version of the story is, in a capsule, Curiosity approaches Mars, slamming into the atmosphere at thousands of miles per hour. The heat shield takes account enormous drag and air resistance and heat as it blasts through the Martian atmosphere. Doesn't slow down enough. So it activates a giant parachute and feels even more drag. That slows it down some, but not far enough. So then they cut the parachute away and switch to rockets to slow down even a little bit more. Now, they can't come down on rockets because rockets would make an enormous dust cloud that would blind the landing pod. So they decide to instead to hover and go down on wires. So the sky crane, these wires lower the Curiosity rover down. It touches against the surface of Mars. Now this thing is heading on a crash course for Curiosity, so it cuts away and flies and crashes somewhere else. It's amazing to think about, and what's even more amazing is that this thing actually worked. Here's an actual picture of the Curiosity rover actually sitting on Mars. You can see right here some damage on the tread where parts have broken off because it's been cruising around the planet for several years now. Science is really awesome. So, what about the forces that it took to get us there? Well, a partial list. We had wind and air resistance and drag. We had friction. We had rockets. We had thrust. We had force from the surface of Mars pushing it back against the rover. We had tension in the wires in the sky crane. We had a lot of things that are happening. Now, the definition of force we used last time was any push or a pull is a force. But one big surprise from physics, all these things that I've listed, I haven't listed gravity yet, but all these things that I've listed are not fundamental forces. Because at the end of the day, they're just one atom interacting with another atom. Any kind of wind or tension or force from the ground, that's atoms bouncing off of atoms. So that's electrons in those atoms interacting with electrons in the other atoms, and those electrons repel other electrons. Never forget that stuff, including you, is 99.99999 something empty space. The nucleus is really small, and the electrons fly a vast distance away from it, and they repel each other. Anytime I interact or feel anything, it's just the electrons in my finger repelling the electrons in something else. So these are just various forms of the electromagnetic force. Now we have gravity. That's fundamentally new. What else is there? Well, it turns out that there are only 4 fundamental forces in the universe. So think of it this way. I've got the gravitational force that holds the universe together. It makes the Earth go around the sun, it makes the moon go around the Earth, and it sticks me to the Earth, and all of the stars in the galaxy and all the galaxies in the universe, they're stuck together with gravity. Then we have the electromagnetic force. Now that's the force that holds the atom together, because it makes the negative electrons orbit around the positive nucleus. If there were no electromagnetic force, there would be no atoms and no chemistry and no life. So it holds the atom together. Now I've got the strong nuclear force. That's the force that holds the nucleus together. How do I take a bunch of protons and pack them into a small space? Well, it's the strong force that makes that happen. Without the strong force, we'd only have hydrogen and no other elements on the periodic table. So again, no chemistry and no life. So we need that. Then the fourth force, the weak nuclear force, that's the one you can't explain to your non-scientist friends. It has to do with some radioactive decay. It's handy in a lot of interesting nuclear processes, but it doesn't come up a lot. So even though you can make a list of a dozen sort of forces that you feel in your everyday life, there are only 4 fundamental forces, fundamentally new ways that things can behave. Now, one quick aside here. Some textbooks, like the one I'm currently using from my algebra physics class, smooshes number 2 and 4 together into the electroweak force, and they say there's only 3 forces. Yeah, you really don't want to do that. I've been doing particle physics and nuclear physics for about 20 years. Trust me, everyone says there's 4. I took classes in grad school from the guy who won the Nobel Prize for working on the electroweak theory, and even he says there's 4 forces. Trust me on this one. Some physicists hope that we'll eventually find there's only one grand unified force that lumps all 4 of these together, but that's just kind of speculation for now. So what we're going to do is talk about some forces. We'll talk about gravity as the only fundamental force that we're going to mention in this series. The electromagnetic force and the strong force and the weak force we're actually going to save for further on down this journey. But we can also talk about some non-fundamental forces like tension and friction and see how we can deal with those. So what we're going to do in this series, we'll take a look at several specific examples of some forces so we can use those to calculate F, put that into F equals ma, and then you've got some good power. All right, so force number 1 for today, gravity. Idea is really simple. Every particle in the universe exerts an attractive force on every other particle. There's absolutely no way we can stop it or shield it or block it. In a fundamental and real way, your body is connected to everything in the universe. Something happens on the moon, it gets interacted with the atoms in your brain and your pancreas and your big toe. We can't stop it. Now, it took an amazing leap of imagination for Newton to realize that the same force that makes apples fall down from the tree is the same force that makes the earth go around the sun. And it's amazing that these 2 really different scales have the same phenomenon behind it. So let's look at his equation. So I've got the law of Newton's universal theory of gravitation. So force is some constant, and here's the number worked out, mass 1 times mass 2 divided by the distance between them squared. So if I've got 2 objects, 1 and 2, I plug in their masses in kilograms, I take the distance between them in meters, and because my constant g here has units of Newton meters squared and kilograms squared, I got to use kilograms and meters, else my units are going to cancel out, not in a good way. It took over 100 years when Newton wrote this theory down to actually measure g, because back in the 1600s, we didn't know how heavy the moon was or the earth was. We had some guesses, but it took a while to get that down. Another thing that's a big help for us for gravity is realizing that if my object 1 feels a gravitational tug from object 2, well, object 2 gets a gravitational tug from object 1, and these things are equal and opposite. Remember Newton's third law? So whenever I jump, I get pulled back to Earth real quickly because of the gravitational force from the Earth on my body. But when I'm sitting there in free fall, I'm putting the exact same equal and opposite gravitation on the force to suck it back up to my feet. Now, we've been thinking about gravity as being F equals mg, where g is 9.8 meters per second straight down. Not just giving you this big, horrible, complicated formula. Are these 2 things the same? Are they different? Can I use one? Can I use both? Let's take a look at this. So, simple setup. I'm going to have an object of mass m. It's above the surface of the Earth, And let's actually use Newton's law to calculate it. Now, if I were sitting really close to the surface on the Earth, not way up above it, and if my object were fairly small, not, the size of Greenland like it is here, but some tiny little dot, from Newton's law of gravity, I would get g, and I'd have this m here for the mass of my object, and then I'd have the other m would be the Earth, so I got the mass of the Earth up here. The distance between them, it's the distance from the center of this object to the center of that object. That'd just be about the radius of the Earth if this thing were sitting on the surface of the Earth. And g and the mass of the Earth and the radius of the Earth squared, these are all constants. So the force is the mass of my object times a whole bunch of constants. Well, I can break our calculators out and multiply these things together, and these constants work out to be 9.8 meters per second per second. So when I say that the an object falls because of gravity and its acceleration is 9.8, we see that this number here, this 9.8, comes from Newton's universal law of gravitation with values plugged in for the mass of the Earth and the radius of the Earth. So this value of g, little g, this 9.8, is just an approximation of the acceleration due to gravity for objects near the surface of Earth. So in summary, Newton's universal law is always true. Approximately true, I can simplify this by plugging in that this is the mass of the Earth and this is the distance of the Earth, and use F equals m times 9.8 straight down. Now in either case, I can take these forces and plug them into Newton's second law, F equals ma. And if I said mg equals ma, the m's cancel, and I can prove that all objects accelerate the same regardless of their mass. Gravity always provides the same acceleration. We've actually been doing that assumption for a long time, but now we can actually prove it mathematically. Okay, one other fun game. What if I leave Earth and go to a different planet? I can just take this formula here with a different value of the mass of that object and its radius, and I can calculate what gravity would be on other planets. Now here we've taken that acceleration and divided it by 9.8 so we can see how that compares to Earth. But I see the Curiosity rover on Mars right now, its gravity is about 1/3 of what Earth's gravity is, whereas on Jupiter it's about 2.5 g. Imagine what that would feel like. As an extreme example here, if we were to go outside a neutron star, which is the mass of the Sun in 5,000 meters, the acceleration would be about 540 billion times what it is on Earth. So what I want to do now is take gravity and let's apply that to stuff. So what we're going to do is talk about another force called the normal force, the second force that we're discussing today. The idea is actually really simple. Let's take an object like this cinder block sitting on a table. There's a force of gravity pulling it down. Well, why isn't my block accelerating? Because there's an equal and opposite force from the table pushing back up on the block. So I've got my diagram here, what we call the free body diagram. Weight pulling down, this other force, the normal force from the table pushing it back up. Now in math, the word normal means perpendicular. So this force from a surface pushing back against the object is perpendicular, so that is sitting at a right angle to my surface, which is where that force gets its name from. Now this force is adjustable. The more I push down on the table, the more the table pushes back on me. Think about Newton's third law here, so that my object isn't moving. And the harder I push, the more the normal force grows to fight that back, until I push so hard I actually break the darn table. And then, well, we're at a table. Now remember with the normal force, they're always perpendicular, that is, normal to the surface. The normal forces are normal, not always straight up. So if I've got an object sliding down a ramp, the normal force is at a 90-degree angle to the ramp, not straight up. So now we can use this to think about why do, say, objects roll downhill? So let's think about the forces acting on this ball. I've got weight going straight down because gravity points down towards the center of Earth. I've got my normal force that's perpendicular to my surface. So now let's think about breaking these vectors off into components, just like we've been doing since the beginning of this video series. Now, when I've got an object that's on a ramp, I want to define a new coordinate system that points parallel and perpendicular to the ramp, not horizontal and vertical. So here's what I mean. My ramp is sitting at this angle, so this angle is now going to be my x-axis. Now, perpendicular to the ramp is going to be my y-axis. So when I set up this way, my normal force is pointing only along my new y-axis, and my weight vector, which is going straight down, has a component that's parallel to the surface and perpendicular to my surface. So now let's think about this. If I were to take my weight vector and I take my angle theta here that I'm inclined, well, this side is adjacent to my angle, so my weight times cosine theta, this vector has to perfectly cancel out my normal force. It keeps my object glued to the surface. There can be no net force in this y-axis because my object isn't flying off the ramp or falling through it. Now, this bit of weight, that must be my weight times sine theta, because this side is opposite from my angle theta. This is a force now that's pushing me down along the surface. It's parallel to the surface. It's going to make me actually go forward. So what I get now in my vector components, I get the weight and the normal force here in my y direction are canceling each other out. But my weight in the x direction is actually making me roll downhill. Now this goes as my weight times sine theta. So when I'm sitting on a flat surface, theta is 0, and I don't roll anywhere. You can do this in all sorts of circumstances, as long as you draw a good diagram, make your vectors work out, and do vector work like we taught in this video for vector addition and vector components, you'll do just fine. The third force we're going to talk about today is static friction. So now let's say I've got an object sitting on a ramp, but it's not going anywhere. Well, why not? That's because friction is keeping it stuck. If I've got a force where something is going to slide against a surface, but it's not going anywhere, that's because static friction is resisting that motion. This diagram here on the left, we've got a hand that's pulling on this block and it's not going anywhere yet. So he pulls harder and there's more opposing force. It's still not going anywhere yet. You remember Newton's third law yet? But if we pull really, really hard, my static frictional force can't get big enough to match, and now the block starts to slide off to the right. Now this behaves a lot like the normal force. Remember, if I had an object sitting on my table, the normal force grows to perfectly match and balance the force of the gravity pushing down on it. And it will grow to adjust to keep my object stuck on the table until it reaches its maximum value where the table breaks and it can't get any bigger. Well, static friction does the same thing. It's going to repel the motion as much as it can to exactly balance out the external force. If my friction were bigger than my pulling force F, then the block would suddenly spontaneously accelerate to the left on its own, and that would be weird. Nature doesn't let you do that. It's only going to grow to perfectly cancel out the pulling force until I've reached my maximum and I can't fight it anymore. Then the block starts to go. So remember, the static frictional force can have any value from 0 up to some maximum. And the maximum is pretty easy to calculate. I just take the normal force, what we're calling Fn here, times some coefficient. Now this is the Greek letter mu. I'm going to use the coefficient for static friction because it's the frictional force. Now once the object starts to move, I now switch from static to kinetic. So you remember, kinetic has motion. That's why the word cinema is pictures that move, or a kinesiology major studies motion. So now once it starts to move, I switch from static friction to kinetic frictional force. It's the exact same equation, except I have a different coefficient here. It's my mu k, not mu s. My normal force is the same, but unlike the static force, my kinetic force doesn't adjust. It's always constant, so it's a lot easier to deal with. Now for any material, mu k is less than mu s, which means once an object starts to move, there's less kinetic friction than there was static friction. Now you know this from common experience. If I'm trying to push a heavy object to make it slide across the ground, once it starts to move, it's actually a lot easier to keep it going. For any homework problem you have, you'll either be trying to calculate what mu is based on the conditions. So you can say, I've got an object sitting on a ramp and it's not moving because static friction's keeping it there. Calculate what mu is. Or you just look up mu in a table and it turns out that mu is only based on the two materials. So is it wood sitting on wood, or metal on metal, or rubber on concrete, or feet on ice? You can look it up on a table. Google has a good list for you, and plug in the number there. All right, the last force in this video, tension. Tension is in a lot of ways the easiest force. It's easier than friction. There's only two simple rules to know. So if I've got some kind of cable or rope or wire that we're pulling on, so number one, the magnitude of tension is the same everywhere along the rope. So if the hand is pulling with a tension force T over here, the magnitude of my tension force is the same right here at the block. Number two, the direction of the tension vector always points along the rope. So here's an example. Imagine I've got some kind of pulley. If this guy is pulling down with a tension force T, this tension force follows along the rope in the direction of the rope to make this object with going upwards with a tension of T. So if you remember that the tension points along the rope, this will be pretty easy. That should make sense though. He can't pull up on the rope to make the object accelerate sideways. Tension force points along the direction of the rope. Now, to make life easier, we never worry about things like the mass of the rope or the mass of the pulley or friction on the pulley. So you're going to get a bunch of ridiculous sounding homework problems that start with words like, a massless rope pulls through a frictionless massless pulley. That just says, let's keep it easy for now, because life is hard enough without having to deal with these details. Alright, so in this video, we talked about gravity, and by extension weight, which is the word in physics for the force of gravity acting on an object. We talked about the normal force, that's the force perpendicular to the surface, usually fighting against gravity. We talked about friction, static and kinetic. Both have the same equation, F equals mu times the normal force. And then we talked about tension. Now the basic idea, again, is you take these forces that you can calculate what the force is, plug them into Newton's second law to do F equals ma, and then figure out what's going to happen. We'll do some examples of this next time. Thanks for watching.